Today our topic is actually fold bifurcation, fold bifurcation for discrete system. Okay, discrete system. So we say that, okay, so suppose we have a map, okay, f of x alpha, where alpha belongs to R and x belongs to R in general. Then we say that system has fold bifurcation. Okay, system has fold bifurcation if it has mu, which is actually f of x at alpha is equal to 0 and fixed point x is equal to 0 is 1. Okay, this is the condition, this is the main game, but definitely we will talk about the generic condition. But before that we are going to discuss the normal form of the fold bifurcation. So normal form is actually that we have a map f of x is going to f of x alpha, which is nothing but this is alpha plus x square. Okay, so now for fixed points, since it is a map, so by the definition of fixed point we will say f of x alpha is actually x. So this means that alpha plus x square is actually x, and this means that x square is actually minus alpha and x is actually plus minus square root of minus alpha. Alpha is less than 0. Okay, less than or equal to 0. But here we will add a condition, and the condition is that we assume alpha is sufficiently small enough. Okay, sufficiently small. Okay, so now we are going to discuss the stability. So if alpha is actually 0, clearly x is equal to 0 is a fixed point, but so it alpha is equal to 0 f of x, okay, at x is equal to 0 is nothing but this is 1, and which is a non-hyperbolic point, so this means that if the eigenvalue for the discrete system is 1 or minus 1, we cannot determine the stability. So that is called actually the non-hyperbolic point. So a point is said to be hyperbolic if the eigenvalue is not equal to 1 or minus 1. Any value that is not 1 or minus 1 is actually hyperbolic value. And similarly, in the case of the continuous system, a value is called hyperbolic if eigenvalue is not 0. If eigenvalue is 0, or if the real part of the eigenvalue is 0, then it is called a non-hyperbolic point. Okay, so now we cannot determine the stability for this one, but f of x alpha is nothing but 1 plus 2x. So f of x, okay, if we do the point, okay, minus alpha, what is this? 1 plus 2 square root of minus alpha. no matter how small alpha is, this value is always greater than 1. So square root of minus alpha is unstable. Okay, and f of x of minus alpha is 1 minus 2 square root of minus alpha. It is clearly less than 1. So square root of minus alpha is stable. Okay, but if we see the bifurcation diagram, okay, if we see the bifurcation diagram, okay, so this is my, okay, so this is my x is equal to square root of minus alpha, unstable. Okay, unstable. Okay, but this is actually x is equal to minus square root of minus alpha, stable. Okay, so this is stable. So this is the bifurcation diagram. Now we can do the same analysis. We can do the same analysis. We can do the same analysis for x. This is alpha plus x minus x square. Okay, this is your homework. But now this when so that the example that we did was just when x was in R1. So how we will know if x is in Rn if we have general fold bifurcation system? If we have general system, how we will determine that okay it does have a fold bifurcation? So that's a very important thing. So suppose how we will know if the system has a fold bifurcation. So that's that we have conditions which is very important. Suppose, so we will see that okay, so suppose x is f of x alpha belong to R, x belong to Rn, okay, has it alpha is actually 0, the fixed point x naught is actually 0. Okay, and then we say that let mu as we define it, f of x at alpha is equal to 0 and fixed point x naught is equal to 0 is 1. Okay, but be careful that for system, like for different system, it's not necessarily required that okay every time we will have fixed point x naught is equal to 0, but this what our supposition, this is just for the simplification. Okay, so now suppose if we have x naught is equal to something else, surely the let mu will be f of x, whatever the alpha value and whatever the x naught, we should get 1 always. Okay, but there's for simplification that alpha is equal to 0, our fixed point x naught is equal to 0, and at that alpha naught is equal to 0, x is equal to 0, our mu is 1. Okay, so this is 1. Then if the following satisfies, okay, if following satisfies, then if following satisfies, and the following number in the following, first one is that f of x, since our alpha naught was 0, x is 0, should be non-zero, the second derivative. And the second condition is that f of alpha, you take the derivative with respect to alpha at alpha naught value, and at x naught value this should also be non-zero. Then the system has fold bifurcation. Okay, fold bifurcation. So we can see that all the two conditions were satisfied for the example one. So in our case, in our last example, so our f of x alpha was definitely 1 plus no, surely. So it was our f of x was alpha plus x square. Okay, so what was mu? So mu was the take the derivative of x with respect to x, so 1 plus 2x. Now at what value of x this f of x is 0, so definitely f of x 0 is actually 1. Okay, but definitely we have to find the alpha value because we don't know the alpha value that at what value of alpha this is, but for any value of alpha this is actually 1. So if we take the second derivative, this is 2 and it is not 0, and also f of alpha is 1, this is also non-zero. So we have fold bifurcation. Okay, so that's how we use this theorem. So if for general system, if these conditions satisfy, then we be sure that okay, the system has fold bifurcation. That's it for today. Thank you.